Welcome to the Platform Engineering Playbook podcast, where everything you hear is built, reviewed, and improved by AI, by me, and by you, the listener. This show keeps me, and hopefully you, up to speed on the latest in platform engineering, SRE, DevOps, and production engineering. It's a living experiment in how AI can help us track, explain, and discuss the fast-moving world of infrastructure. Every episode is open source. If you've got something to add, correct, or challenge, head to platform-engineering-playbook.com. You'll find all the content and a link to the GitHub repo. Open a pull request, join the conversation, and make the playbook smarter. Let's get into it.
Episodes 1 through 14 taught you the correct way to build multi-region. Aurora replication, DynamoDB global tables, disaster recovery procedures, security controls. Everything working perfectly in theory. But theory and production are different universes. Today you're learning from companies that built multi-region and watched it catastrophically fail, not hypothetical failures. Real outages with real revenue loss and real postmortems. By the end of this lesson, you'll understand the 6 anti-patterns that cause most multi-region failures. Real case studies with specific numbers. Warning signs you're heading toward failure. And recovery strategies when anti-patterns are already in production. Because learning from others' expensive mistakes is cheaper than making them yourself. Let's start with anti-pattern 1, building multi-region without business justification. Company A, a SaaS platform with 20 employees, revenue $8 million annually. Engineering team reads about multi-region, decides we should do this. No calculation, no threat modeling, just assumed it was best practice. They built hot-warm. Aurora Global Database, DynamoDB Global Tables, EKS, in 2 regions, spent 3 months engineering. Infrastructure cost increased from $12,000 monthly to $95,000 monthly. That's $83,000 additional monthly, nearly $1 million annually. From episode 9's ROI calculation, $8 million revenue equals $913 per hour. Their typical outage without multi-region, 2 hours annually. That's $1,826 annual risk. They spent $1 million annually to mitigate an $1,800 risk. 6 months in, board reviewed expenses. Demanded justification for multi-region. Engineering couldn't provide it. Project deemed cost prohibitive. Rollback to single region. 3 months engineering wasted. $1 million spend wasted. Team morale damaged. The mistake. Not running the numbers before building. Episode 9 taught ROI calculation. Revenue per hour times expected outage hours equals cost without multi-region. Multi-region cost minus single-region cost equals incremental spend. If incremental spend exceeds outage cost, ROI is negative. For Company A, $1 million incremental versus $1,800 risk equals a 550 times over investment. They needed 500 hours of outage annually to break even. Impossible for their infrastructure. Fix. Always calculate ROI first. Present to business stakeholders. Get approval. Document decision. Only then start engineering. Anti-pattern 2, split brain scenario causing data corruption. Company B, a financial services startup, built hot DynamoDB global tables for transaction processing, US East 1 and US West 2, both accepting writes. A network partition happens between regions. Both regions continue operating independently. Both think they're authoritative. Customer in US East 1 makes deposit. Balance increases to $1,000. Replication to US West 2 blocked by network partition. Customer in US West 2 makes withdrawal. Balance decreases from previous 500 to 300. Writes continue in both regions for 10 minutes. The network partition heals. DynamoDB conflict resolution uses last writer wins based on timestamp. US West 2's withdrawal timestamp is newer. It wins. US East 1's deposit is overwritten. The customer's $1,000 deposit is lost. Corrupted account balance showing 300 instead of 1,300. This happened to 400 customers during the 10-minute partition. Total lost deposits, $600,000. Manual reconciliation from audit logs took 2 weeks. Customer trust damaged. 300 customers closed accounts. The mistake, not designing for eventual consistency from episode 10. DynamoDB is AP, availability and partition tolerance. During partitions, consistency is sacrificed. Last writer wins doesn't understand business logic. Deposit plus withdrawal equals an incorrect final state. Fix from episode 10. Use application-level versioning. Every write includes an expected version number. Detect conflicts, handle an application logic, or use Aurora for transactions requiring ACID guarantees. The CP model prevents split-brain writes. Warning sign. Seeing DynamoDB conflict metrics increase in CloudWatch. Conditional check failed exception errors spiking. These indicate writes are conflicting due to race conditions or replication lag. Investigate immediately. Anti-pattern 3. Untested failover discovered during an actual outage. Company C, an e-commerce platform, built a beautiful, hot-warm multi-region following all episode guidance. Aurora Global Database, EKS, Route 53 health checks, documented runbooks. Looked perfect in architecture reviews. They tested it once during initial deployment. It worked. They never tested it again. 18 months pass. Engineers who built it leave the company. A new team inherits a multi-region they don't fully understand. Black Friday. US East 1 experiences regional degradation. Not a total failure, a partial one. Some AZs healthy, some not. Route 53 health checks hit a healthy AZ, report the primary is healthy. But most traffic is hitting the unhealthy AZs. Error rate is 30%. Revenue is dropping. The team decides to manually fail over to US West 2. They follow the runbook. Step 1. Promote Aurora secondary. The command fails. Error KMS key policy doesn't allow US West 2 to decrypt. The original engineers configured per region keys but forgot to add failover permissions. 20 minutes troubleshooting KMS. Finally update the key policy. Retry Aurora promotion. Success. Step 2. Update Route 53. They changed the record to US West 2. Wait for propagation. 5 minutes pass. Traffic is still hitting US East 1. They realized the TTL was 300 seconds, not 60. Original engineers changed it years ago for cost optimization. 15 more minutes waiting for DNS propagation. Step 3, scale EKS secondary. They increase the pod count. Pods start but go into crash loop back off. Secrets Manager replication was disabled 6 months ago during a cost-cutting initiative. The pods can't retrieve the database credentials. The secondary region is broken. Total failover attempt time, 90 minutes. It should have been 5 minutes from episode 12. Revenue loss during those 90 minutes, $2 million. They eventually fixed Secrets Manager, scaled the pods, and traffic shifted. But the damage was done. Post-mortem finding, runbooks were outdated. The quarterly DR tests from episode 12 weren't happening. Cost optimizations broke failover without anyone noticing. The team didn't understand the architecture deeply enough to troubleshoot. Fix. Game day exercises quarterly, mandatory, not optional. Test the complete failover end-to-end. Document every step. When infrastructure changes, verify DR still works. Automate DR testing to prevent drift. Anti-pattern 4. Operational complexity exceeding team maturity. Company D, a startup with 5 engineers, none with Kubernetes production experience, decided to build hot multi-region with an Istio service mesh from episode 11. Month 1. Set up EKS clusters. Deployed Istio. The configuration is complex. Envoy, Pilot, Citadel components. Istio debugging is its own skill. Engineers spend 40 hours reading docs. Month 2. Deploy first application. Traffic routing doesn't work. Spent 1 week discovering a virtual service misconfiguration. One senior engineer becomes the Istio expert out of necessity. Others can't debug mesh issues. Bus factor of 1. Month 3. Intermittent failures. The Envoy sidecar is crashing. Memory pressure. Istio overhead is consuming 30% of pod resources. Need to increase instance sizes. Cost doubles. Month 4. Certificate rotation breaks prod. The Citadel cert expiry wasn't monitored. The service mesh loses mutual TLS. All pod-to-pod communication fails. Outage for 6 hours. The team doesn't understand Citadel well enough to fix it quickly. Eventually, they redeploy the entire mesh. Month 5, CTO reviews engineering velocity. Feature development is down 70%. Engineers are spending most of their time on infrastructure, not the product. Competitors are shipping faster. The board is concerned. Month 6, decision to rip out the service mesh. Return to a simpler architecture. No Istio. Basic EKS with an ALB. 4 weeks migrating off the mesh. All that complexity for zero business value delivered. The mistake. Adding complexity the team couldn't support. A service mesh adds capability from episode 11, but it requires expertise. A 5-person team without Kubernetes depth couldn't operate it reliably. The operational overhead exceeded their engineering capacity. Fix. Match complexity to team maturity. Start simple. Basic multi-region with Route 53 failover. Add complexity only when you have the operational skill to support it, or hire an experienced SRE before deploying complex systems. Warning sign. Engineering velocity declining after a new infrastructure deployment. More time is spent debugging the platform than building features. This indicates the operational burden is too high. Anti-pattern 5, cost explosion from unmonitored replication. Company E, a media platform. Enabled DynamoDB global tables on all tables. 20 tables total. Seemed reasonable following episode 6 guidance. Month 1, infrastructure cost was $28,000. Up from a previous $19,000. A $9,000 increase attributed to multi-region. Expected. Month 2. Cost jumps to $42,000. A $14,000 additional increase. Finance asks why. Engineering doesn't know. Too busy shipping features to investigate. Month 3. Cost is $61,000. $33,000 above baseline. Finance escalates to the CTO. Emergency cost review. Engineers dig into AWS Cost Explorer. Discovery. DynamoDB global tables write capacity units are through the roof. Traffic increased 20%. But DynamoDB costs increased 200%. They investigate. Root cause, one table, user sessions, had high write volume. Every user action writes to the session. With 3 regions and global tables, every write costs write units in 3 regions plus replication units. 5 times the WCU cost from episode 6. The session table alone was costing $18,000 monthly. Additional finding. A logs table was replicated globally. 500 gigabytes per day of writes. Every log entry written to 3 regions replicated twice. Total WCUs were astronomical. The logs table was costing $12,000 monthly. They fix it. Remove user sessions from global tables, make it regional. Remove logs from global tables entirely, use CloudWatch with S3 export. Cost drops from $61,000 to $32,000 monthly. But 3 months of overspend. $96,000 wasted. The mistake. Enabling global tables without understanding the cost implications. Not monitoring cost per table. Not calculating WCU usage before deploying. Fix from episode 9. Selective replication. Only tables requiring active need global tables. User sessions don't need multi-region writes. Cost monitoring per service. Set billing alerts. Review cost weekly during the initial deployment. Anti-pattern 6. A single region mindset causing production failures. Company F built multi-region EKS US East 1 and US West 2. The architects designed it like a single region with failover. They didn't consider cross-region latency, replication lag, or network costs from episodes 5 and 7. Their architecture, front-end in both regions. API service in both regions. Database was Aurora primary in US East 1, with a secondary in US West 2. The design assumption, requests complete within the same region. Front-end calls the local API. API calls the database. Reality in production. Route 53 latency routing sent California users to US West 2. The front-end in US West 2 called the API in US West 2. The API made a database call to the Aurora primary in US East 1. A cross-region database query on every single request. 65 milliseconds of cross-region latency was added to every query. With 50 queries per page load, that's 3.2 seconds of added latency. Page load times exploded. Users complained. Conversion rate dropped 15%. Revenue impact, $30,000 per day. Engineers added read replicas in US West 2 for reads, but writes still went to the US East 1 primary. Write operations were slow for West Coast users. Checkout failures increased. They hadn't designed for a distributed architecture from the start. Additional problem, data transfer costs. The front end in US West 2 making 50 database calls to US East 1 per request. 10 gigabytes per hour of cross-region data transfer. 2 cents per gigabyte equals 48 cents per hour, $348 daily, $10,000 monthly just for front-end to database traffic. The mistake, not designing for distribution from episode 1. Multi-region isn't single region plus failover, it's fundamentally distributed. It requires thinking about data locality, replication patterns, and cross-region costs. Fix, design assuming distribution. Keep read traffic local using read replicas. Route writes to the primary, but optimize write frequency. Consider active-active with DynamoDB for better write locality. Or accept higher latency for consistency. Before we wrap up, pause and answer these questions. Question 1. A company has $10 million in annual revenue. Multi-region adds $75,000 in annual cost. Their typical outage risk without multi-region is 3 hours annually. Should they build multi-region? Question 2. You're seeing conditional check failed exception errors increase in your DynamoDB Global Tables CloudWatch metrics. What does this indicate? Question 3. Your 5-person engineering team is spending 60% of their time on infrastructure and 40% on features. What's the warning sign? Take a moment. Answers. Question 1. No $10 million in revenue equals $1,140 per hour from episode 9. 3 hours of outage equals a $3,420 cost. Multi-region costs $75,000. That's 22 times more than the risk. The ROI is negative. Better to optimize single region reliability, maintain good backups, and have an incident response plan. Multi-region isn't justified until the expected outage cost approaches the multi-region incremental spend. Question 2. Conflicts from concurrent writes or replication lag. Multiple regions are writing to the same item simultaneously, or writes are conflicting before replication completes. From episode 10, this is AP system behavior. You need application-level conflict resolution with version numbers, or you need to switch to the Aurora CP model for ACID guarantees. Question 3. Operational complexity exceeds team capacity. A healthy ratio is 80+% feature work, under 20% infrastructure maintenance. When that's reversed, the platform is too complex for the team size. Fix by simplifying the architecture, hiring platform specialists, or focusing on stabilization before adding more complexity. Let's recap what we covered. First, anti-pattern 1. Building without business justification. Calculate ROI before engineering. Present 2. Stakeholders. Document decision. Company A wasted $1 million on multi-region for an $8 million revenue business with minimal outage risk. Second, anti-pattern 2. Split-brain scenarios causing data corruption. DynamoDB eventual consistency with last writer wins lost $600,000 in deposits during a network partition. Designed for an AP model with application-level versioning or use a CP model with Aurora. Third, anti-pattern 3, untested failover. Company C's Black Friday 90-minute failover should have been 5 minutes. Outdated runbooks, broken secrets manager, wrong DNS TTL. Quarterly game day testing prevents this. Test failover every 3 months. Fourth, anti-pattern 4, operational complexity exceeding team maturity. A 5-person team couldn't operate an Istio service mesh. Engineering velocity dropped 70%. 6 months wasted. Match complexity to team capability. Fifth, anti-pattern 5, unmonitored cost explosion. Company E's DynamoDB costs tripled over 3 months. Global tables on high write tables without calculating WCU implications. 96,000 wasted. Monitor costs weekly during deployment. Sixth, anti-pattern 6, a single region mindset in a distributed deployment. Company F added 3 seconds latency and 10,000 monthly data transfer costs by not designing for data locality. Treat multi-region as a distributed system from day one. Remember the course journey? Episode 1 established foundations, the CCC triangle, why multi-region exists. Episodes 2 through 11 taught technical implementation. Episodes 12 through 14 covered operations, compliance, security. Now, episode 15 shows what happens when you skip steps or ignore principles. These aren't edge cases. These are common failures. Next and final episode, the 90-day implementation roadmap. You've learned everything multi-region. Now the question, where do you start? How do you go from single region today to production multi-region in 90 days? You'll learn the 4 phases: assessment, foundation, replication, and validation. What to build in which order, when to cut over to multi-region, how to validate each phase before proceeding, and the go-no-go criteria. When to abort if reality doesn't match the plan. Because having knowledge is different from executing a plan. Let's turn 15 episodes of learning into a concrete implementation timeline. See you in episode 16.
That's it for this episode of the Platform Engineering Playbook podcast. Every topic, transcript, and summary you just heard lives out in the open at platform-engineering-playbook.com, where anyone can suggest updates or add insights through GitHub. If you've got thoughts, fixes, or new ideas, open a PR. And if you enjoyed the episode, rate us on your favorite podcast platform. We're always shooting for 5 stars. While you're there, give the project a star on GitHub. It helps others find and contribute to the Platform Engineering Playbook. This podcast is generated by AI, reviewed by AI, me and you, a community of engineers keeping our craft sharp. Thanks for listening, and see you next time inside the Platform Engineering Playbook.